Hello everyone, and welcome to our latest episode of SNIA's Everything You Wanted to Know About Storage, but We're Too Proud to Ask webinar, part per million. What if programming and networking had a storage baby? This is a very special treat today, because not only are you going to be watching the webinar with the longest title in the series, but we've got some of the industry's top experts acting as our neonatal nurses for you. Before we get started on today's webinar, let me go over a little bit of administrivia for you. First, if you find yourself having problems with the audio cutting out, we've found that this often is an issue with various browser caches. Emptying the cache or reloading the browser often helps. Second, the information contained in this presentation is copyrighted by SNIA, and any member company and individual members may use this material in presentations and literature as long as the slides are not modified and SNIA is acknowledged as a source. Feel free to use the question button at the top of the screen to ask anything you like. We will do our best to answer them in the time allotted. However, I should probably warn you that we have so much content today that we may not be able to get to too many of the questions. Nevertheless, we will eventually answer those questions in a blog after the seminar. Also, please do not forget to rate this presentation. Constructive comments in particular are most appreciated. If you have any concepts or topics that you would like to see in the future, that's also the best place to put them. Last but not least, this presentation will be available along with a blog that addresses all those questions at a URL that will be posted at the end of this presentation. So, as I promised, the proper care and feeding of today's storage baby are going to be nursed by some of the industry's most capable engineers, and I'm going to have them introduce themselves. So, Alex?
Good morning, good afternoon, good evening, good wherever you are, ladies and gentlemen. My name's Alex McDonald, and I work for the Office of the CTO at NetApp. Part of my responsibilities include working with organizations like SNIA, where I work on the CSI, the Cloud Storage Initiative, the SSSI, Solid State Storage Initiative, and this group, the Ethernet Storage Forum.
Dror?
Hello everyone, my name is Dror Goldenberg. I'm based in Israel. I've been working in Melanox for 17 years, and my main focus is on software architecture for storage and for networking.
Rob?
Hello everybody, my name is Rob Pegler, and I'm the Senior Vice President and CTO of Symbolic.io. I also serve as a member on the Board of Directors of the SNIA.
And my name is Jay Metz. I'm a research and development engineer for storage for Cisco, and I also act as a member of the board of directors for SNIA as well. So, speaking of SNIA, in case you're new to the organization, we are an industry association that represents 160 unique member companies, with over 2,500 active contributing members that reach a community of over 50,000 IT end users and storage professionals worldwide. Of course, there's always room for one more. So feel free to look into joining us because we'd love to have you. As far as today's seminar is concerned, we're going to be looking at the place where storage exists at the intersection of programming and networking. In particular, we're going to be looking at 4 specific parts of storage that people are usually expected to know, especially when we talk about subjects like persistent memory, clustered file systems, or modern transport protocols such as NVMe over fabrics. But in order to talk about those topics, we need to talk about and know these first. Specifically, we'll be talking about the differences between block, file, and object-based storage. Understanding block storage in particular is very handy to understanding logical block addressing, especially as we compare it to Byte addressable storage. The next thing we'll be talking about is POSIX as it relates to storage, which is one of those topics that many people already know, or at least pretend to know. Finally, we'll be looking at the differences between log structures and journaling systems, which will help us understand how we keep track of what we're writing to and where. So, without further ado, let's begin at the beginning with some basics of block, file, and object storage. Now, for many of you, this may be a no-brainer. But since this is the Too Proud to Ask series, it's useful for all of us to be on the same starting page. Generally speaking, there are 3 types of storage access. each has a very distinct characteristic when it comes to the relationships to hosts. The hard part comes when we use these terms in different contexts. For instance, when we talk about blocks on a disk, we're not talking about the same type of blocks that a file system sees. And when we talk about file systems, it's not really the same thing as file-based storage system. So, what is block storage? Block storage is the foundation for all storage systems. All storage, whether it be file-based or object-based, eventually winds up being block storage at the lowest common denominator. If you'll forgive the pun, it's the fundamental building block upon which all storage is built. Now, the closer you get to accessing block storage directly, the more powerful and performant the system is. This means that block storage is very fast, but it's also very unforgiving. Block storage is used for booting servers and virtual machines, and is the preferred method for highly transactional workloads, such as databases. The double-edged sword, though, is that while it's extremely high-performance storage, it's also somewhat fragile. It relies very heavily on the redundancy at every level of the architecture for that high availability that we rely upon. What's more, because it's a strict one-to-one relationship between a host and the storage itself, it makes it very difficult to scale or to share. In contrast, file-based storage is more abstract. A file can be made up of one or more blocks and then logically accessed by a symbolic name. The SNIA definition here goes a bit deeper than we're looking at for this particular webinar, but I'm including it for completeness. Essentially, the key thing to keep in mind here is that the definition of a file will come back to us in the next section, especially the part where it's an ordered sequence of data bytes and a symbolic name by which an object can be uniquely identified. That object can be, for instance, a block or a series of blocks as well. Now, of course, file storage is the foundation for network-attached storage, or NAS systems. Both NFS and SMB are known as file because that's their atomic unit for interacting with the host. File storage is everywhere inside of data centers and acts as the common ground for both structured and unstructured data. It's more scalable than block storage because it allows for sharing data among a large number of clients. SNIA has done a number of these webinars on the subject for both NFS and SMB, the foundation for file storage for networking. And I highly encourage you to look at some of those excellent sessions if this is something that you want to know more about. If that information can be found at the SNIA blog link shown at the end of this webcast. And finally, we're going to look at object storage. Now, object storage is all the buzz right now, and with good reason. We're really not going to be focusing too much on object storage for the remainder of this webinar, but it's useful to know in comparison to file and block. Now, the scalability of file systems and the additional power of metadata encapsulate them into a single object, and you can do some amazing things. So object storage is built for scale, plain and simple. It organizes data in a flat structure, kind of like a giant toy box for all of your object toys. And even though there's no file system where you would keep track of all the files in an index or a journal, you have lots of metadata that you can use to find out what you need. So in this case, I want to give a credit to Jeff Lundberg here. I'm shamelessly borrowing his example because the example of object storage is by far the best I've ever seen. If you imagine a grocery store with no labels on any of the cans, you get an idea of the difference between what an object and a file actually wind up being. In our metaphor, the cans would be the file part of the object. The metadata then would be the information that goes on the labels onto the cans. If you didn't have the labels on the cans, you'd have to index the location of each of the cans in order to retrieve that data. In fact, that's roughly how a file system works. Here, though, you can move the cans around. As long as the labels go with it, you can find it again. And over time, the metadata can become even more important than the data itself. Now, the key thing to keep in mind here is that object storage is very, very powerful because it has the ability to be searched and found. That is, the ability to search, find, and analyze information based upon the metadata is an extremely powerful function. Object storage is several layers above block, however. Remember that object storage is made up of files, and files are made up of blocks. And with each layer of abstraction, you gain a performance penalty. So there are trade-offs. With block storage, you get very high performance, dedicated storage that is useful for applications and workloads where the data changes frequently and you absolutely, positively need to have always-on access. File storage is useful when you need to share data across hosts or users and gives you greater flexibility when you need to scale. And object storage is a great option for when you're looking at completely unstructured data, objects that can effectively sit anywhere in the world and don't change very much, if at all. Now, this is a reference slide that you'll be able to look at a later time should you decide to download the presentation for your own perusal. It goes into some of the main comparison types between the different architectures in broad strokes. In the interest of time, however, I'll simply point out that it's here for your use later on. I want to make sure that we get to the real heart and meat of this particular presentation. So, for now, though, I would like to turn this over to Dror, who is going to tell us how to access all that lovely information that we've been talking about. So, Dror?
All right, thank you, Jay. So I'm going to talk about byte addressable versus logical block addressing. So just to start and level set everybody, I want to talk about system architecture to understand how stuff goes together. And in typical system architecture, as you can see on the left-hand side, you have the CPU running some kind of an application. Can be storage application, can be a web application, machine learning, or what have you. And that CPU runs the software that is accessing the DRAM or the peripherals through buses. And we covered buses in one of the previous webinars. And basically those buses have some addressing scheme, and that's what we're going to touch upon in the next coming slides. So it might be addressing for accessing DRAM, might be addressing for accessing storage on peripheral bus. On the right-hand side, just to explain a little bit about byte and block, you can see on the top that a byte means a collection of 8 bits. Each bit can be 0 or 1. And basically taking 8 different bits, collecting them into one byte, enable us to name any number between 0 to 255. So that's total of 256 values. So that's a byte. Remember, a byte is just 8 bits. A block is actually many bytes. How many bytes? Is typical number would be 512. But there are many other blocks depending on the implementation, media, or many other reasons. It can be anywhere from 512 to 1K, 4K, 32K, and even more. So that's a larger collection of bytes, is just one block. For the sake of simplicity, we'll refer to blocks as just 512 byte collections. So let's talk about addressing. So if you look at a picture, basically what address means is a description of the location. So you can see many drawers here, and an address really denotes a particular drawer, and that's the whereabouts of my data. And when I'm talking about byte and block addressing, what do I really refer to? So given the location in the address, the block and byte addressing actually means what is actually stored in that drawer, what's in the box. So when we're talking about byte addressable, then that address really describes a location of a byte. So a byte, again, is 8 bits. And byte addressing is traditionally used for memory. So every time you have a computer program that is accessing memory, the accesses would be on a byte granularity. So that will use byte addressable, and the application will read or write 1 byte. It may obviously do read or write for more bytes, but the smallest unit in granularity that the application can access is 1 byte on a memory. When we're talking about logical block addressing, then we're talking about accesses that are for an entire block. And block is many bytes. We mentioned 512 as a good number for a block, and that's a typical access. The block, the size of 512 bytes is coming from rotating media. It used to be, or it still is, the sector size of a disk. And it's further used in other storage systems that are also solid state. So whenever you're doing a logical block addressing, then your address describes a location of one block, and your access would be to read or write a full block, a full 512 bytes. So you cannot do anything smaller than that. So just to compare the two different approaches. So when we're talking about byte addressable, we're talking about a fine-grained access, 8-bit at a time. When we're talking about logical block addressing, this is more a coarse access. It's often 512-byte blocks. The access API for byte addressing is just a load store of a command. You basically are referencing a pointer and you're storing and loading from that pointer. When you're doing LBA access, then it's typically an IO command that will be a read or write, an API that will enable you to read or write a full block. Just to understand the amount of addressable space, so when we're dealing with 32-bit addressing, then byte addressable covers just up to 4 gigabytes. And even today, I have more than 4 gigabytes on my laptop, so that really explains the reason why industry has moved many years ago from 32-bit addressing into 64-bit addressing. Similarly, in LBA, because of each address describe much a larger chunk of a block, then 32-bit addressing will cover 2 terabyte worth of storage. But again, those numbers are low, and this is why industry is moving to 64 bits. And last, byte addressable is typically used on memory bus, and logical block address is usually used traditionally on storage devices. So I've described those two methods, but there is a new kid in town, which is the persistent memory. So where traditionally memory is fast and volatile on a memory bus, and storage is slow and persistent on a peripheral bus, the new persistent memory or the new storage class memory really breaks those rules. And it really enables something that will be fast like a memory, maybe slightly slower, but still very fast. And it can also be persistent like storage. And that fast storage can be on the PCI bus, or it can be on the memory bus, so it can fit both buses in the system. And it really has some new access and programming models. So for the storage class memory, or for the persistent memory, there are 3 major options to perform access to it. So obviously it's all located on the DRAM bus. The first option is to access it using logical block addressing. So basically you are reading or writing a full block from a non-volatile storage device. So that's a logical block addressing. The second option is to address it like a memory. So it will behave as a volatile memory, and you can read or write on a byte granularity, on a byte addressing, like you do with any other memory. You'll just get maybe slightly slower speed, but much more capacity. And the last option is to access it like storage class memory, which basically means that you're doing byte addressing operation, and you're getting non-volatile. So everything that you store in that byte addressable is persistent. So aside from load and store, you'll have to deal with the persistency, and there's a mechanism to deal with it, and you can take a look at the link below at the SNIA NVM programming model, which really describe all of that and how to deal with persistency on those new storage class memory. So just to summarize, you have the applications that can be any application, like database, caching, storage, web, big data, artificial intelligence, just name it. And application access memory, as you can see on the left-hand side, the access to memory are byte addressable, and they are typically done by doing CPU load store. On the right-hand side, you can see access from application to storage. It may be typically a block storage by doing an I/O read-write with those special APIs for doing a block access. Might be even that they access some higher level, like object or file, but the low level, as Jay mentioned, would be block read and write. And with the new persistent memory or non-volatile storage class memory, You can basically access it the same way as you do with Byte Addressable using load and store. You can use it with the block-based read and write. And last, there is a new API to use them as a persistent device with byte level addressing. So with that, I will hand it over to Alex to discuss the next topic.
Actually, before we do that, I think we have a couple of questions, and we have some time for questions that we can explore. First and foremost, the question about persistent memory came up with, is that like Flash? And I think this is a really good opportunity to go into some of that a little bit. Can you address that, Tor, about persistent memory and Flash, and make that a little clearer?
Sure. So persistent memory is like Flash, but it's not exactly Flash. It's a different technology. Actually, there are multiple technologies to enable that. It can be phase chain memory. Some other implementation are doing it with DRAM and some supercap that will store it into Flash. So there are multiple technologies to achieve storage class memory. Flash can be one of them.
Excellent. And then the other question that is actually to me, on one of the earlier slides I had was regarding the deprecation of the sys nomenclature for the file-based protocol. So it's not SMB that's been deprecated, it's the phrase sys, C-I-F-S, that is no longer used in networking. So when we refer to file-based systems, it's SMB or NFS, and sys is no longer used. So thank you for giving me that opportunity to clarify that question, and I will turn it over to Alex now for POSIX.
Thank you, Jay. Thank you, Dror. So, to talk a little bit about POSIX, I don't know how old any of you are. It's very difficult telling how old your audience is sometimes on these presentations. But I am a bit like Methuselah of exceeding age, and I can remember POSIX the first time round. What was POSIX? Well, if you think way back to the point where people were developing operating systems, in particular Unix, it became apparent probably in the sort of mid to late 70s that things weren't quite going to plan. We'd standardized the programming language. We'd standardized C. We'd standardized a number of others, but C was one of the most popular. It was an algol-based language. And like algol, it failed to standardize a couple of very important features. It failed to standardize how it interfaced with the operating system. And in particular, it didn't do things like how to do locking with semaphores and mutexes, how to manage memory, and how to do I/O. In fact, one of the things that's singularly lacking from the C language standard, if you look at it, is anything to do with I/O, which might seem to be a major mistake, but in fact it's fairly common in programming languages not to standardize the I/O interfaces. So a lot of the good and the great got around and got together and developed something called POSIX, the Portable Operating System Interface for Unix. And the goal was to provide this layer of portability to allow applications to run on one type of Unix versus the other. And at the time, there were a proliferation of Unixes. There were quite a lot of them. And we're actually living through a period right now where there are relatively few, and the market is dominated by two operating systems, Linux and Windows. But in the 80s and 90s, there were an awful lot of operating systems, very many different Unix-type operating systems. So there were a family of standards put together and specified by the IEEE. And you can see the link there. That takes you to the POSIX standards, which also include, interestingly, the C programming language standard as well. So this standard was, in fact, an API or an application programming interface standard. It wasn't language independent. It was very dependent on C. And it specified these API level interfaces for a wide variety of operating systems. The diagram on the right, and I do apologize for the rather sludgy colors and the slight smallness of it, is meant to illustrate that what we have in the core is an operating system, and a wrapper around that, which is the new C library that allows us to do independent of the operating system, calls that are standard and POSIX based, so that applications can actually take advantage of being able to run on one operating system and porting them to another becomes relatively straightforward. So that was the idea behind POSIX. But of course, POSIX has a storage part to it. The storage-related parts were relatively simple. The POSIX layer actually lives above the device driver. Now, when we talked earlier about devices in terms of block addressable devices, and the device driver is simply a piece of code that allows the operating system to talk to that device and to manage that device. Applications generally don't manage their own devices. They talk to the operating system, which manages it on their behalf. So this POSIX layer lives above the device driver, and it's a set of interfaces that talk to the device driver that then talks to the device itself. And what it does, it provides directories and file type structures and data as a stream of bytes over the top of a wide variety of devices. It's not just block structured devices, but those are the ones I'm going to focus on today. The storage devices that we're all familiar with in terms of disks, for example. So these directories and files are a function that the POSIX layer provides. These are capabilities that the POSIX layer provides. And a file and a directory are remarkably similar. A directory is simply a file, believe it or not, all files. It's a file that contains information about files. And the files themselves contain data, and the data is treated as a stream of bytes. It's not treated as a block. It's treated as a stream. I can start addressing it at byte 0 and work my way out to the end. And because I'm talking in the main to random access devices, I can also then move around that file and move back to byte 10 or forward to byte 2,074 as an example. And there are a set of I/O operations that POSIX defines, and probably the 5 or 6 that are commonly used are, and in fact probably 5, I think I/O controls are relatively specialized, but we've got open to open a file, and what that does is it associates a file handle or a transparent or opaque, depending on your point of view about these things, structure that we use to communicate with the underlying device driver. So open does that, associates this file name with a file handle. We get back the file handle. We operate on the file handle, having given the operating system, or the POSIX interface anyway, the file name. We can then read and write to it and move about it. We can seek about it. And then eventually when we're finished, we can close it. And that's not the end of it, though. There are a large number of ancillary calls, for instance, for doing things like locking on the file to make sure I can lock sections of the file while I update it and other people are locked out from it. And a lot of command line interface commands to allow us to manage these files. We can delete them, we can rename them, we can move them from one directory to another. So POSIX made this a lot simpler and made it possible for applications to be relatively operating system independent. The benefits that POSIX brought have been huge over the years. This uniformity of interfaces allowed us to do a huge amount of application development and to develop applications once and then to port them across multiple operating systems. You know, to port them from Linux to FreeBSD to NetBSD to a wide variety of operating systems. And that gives us a simplicity and broad application. The other nice features about POSIX is that it treats data as a stream of bytes. Now that matches quite a lot of devices that you might think of. For instance, in the old days, we had things called teletypes. Nowadays, we've got things like Apple iPhones, and they also produce streams of bytes. And the Internet of Things is providing us with technologies that treat data as a stream of bytes, that we're not dealing here with blocks or objects, we're actually dealing with streams of information that we are sending and receiving from Internet of Things type devices. And the diagram is trying to show that there. So it matches the capability of a wide range of devices. It provides us things like consistency with locking. So in other words, we can ensure that the last writer to a particular area of the file always wins. And that we can do file locking. We can lock an entire file and stop anybody else from doing anything with it. Or we can lock parts of a file. So I can, for instance, build databases over the tops of files because I can lock individual parts of it and treat them as records. It's easy to port applications. Well, easy for some definition of the word easy. It doesn't include the phrase impossible. But it does make it easier to port applications across POSIX compliant systems. And in fact, in some cases, The only porting that's required is a recompilation on the other operating system, and the application will run unmodified. It's stateful. It provides state through this opaque file handle. That allows us to manage it very simply. We know exactly where we are with a file. We know exactly, the operating system in POSIX maintains a file pointer for us. We don't need to maintain it. The file system does that for us. That state is very valuable in making applications a lot simpler. And file systems are pretty ubiquitous, and there are a huge variety of file systems there. But most of them have very similar to identical POSIX interfaces, and that makes them easy to develop for. So we can change the underlying file system, yet not have to change our applications, because they are using these consistent and well-documented POSIX interfaces. Anytime you've got some advantages, you've always got some disadvantages as well. So there are a few downsides of POSIX. The definitions are implemented as a C language API, which is great if you're coding in C. But if you're doing it in other languages like Python or Perl or Camel or whatever your poison of the day is in terms of application development, then you've got different ways of dealing with files. But you should be able to find in common across most programming languages something that resembles an open, something that resembles a close, and something that resembles reads and writes and the ability to seek around the file. It's stateful, so that advantage that we had in terms of the operating system maintaining all the state for us and us not having to be terribly smart about the file because it maintains a lot of information on our behalf, that makes it difficult to scale, and it's not restful. Now, I'm not going to go into what restful is here. There are plenty of presentations out on the web about restfulness. But basically what that means is, if you look at something like, for instance, a RESTful interface that's based on HTTP, something web browsers speak, they don't have any handles. They've just got resource IDs. And they implement the reading and writing and the management of objects, big lumps of data, not individual bytes within a file. And that makes them much easier to scale. I can have millions of them, and I don't have to have millions of file pointers and millions of people trying to get into the same file, for example. It's also network unfriendly. So if you look on the right-hand side, you'll see there's a certain amount of chat that goes on as you open, read, write, and close a file. And that, there are some solutions for that. So for instance, NFS over the years, which is a network file system that allows you to use POSIX-like semantics against network files maintained at the end of the network, has done a certain amount of work in providing compound operations where I can do an open, read, and close in a single operation. But there is that network unfriendliness. It's a bit chatty. And sometimes that statefulness also makes it a little difficult to do recovery. It's quite complex often doing the recovery in the face of errors or in the face of what I think is a fairly common feature of modern life, which is great networks, but sometimes not great network connectivity, and we get errors and we have problems with networks that we have, and that causes file systems a few headaches. And there are other issues that I'm not going into here to do with metadata, to do operation ordering. In other words, if I've got a reader and writer on one system and I've got another reader and writer of the same file on another system, and they happen to be geographically split, and one's a couple of microseconds away in terms of its responsiveness because the speed of light is finite, that can cause us problems. So there are some downsides to POSIX and the way we deal with POSIX storage. However, it's a positive future, because if we think of the three ways we have of dealing with data, we've got block. Now, block is pretty primitive, requires a lot of management, doesn't provide any facilities for building, if you like, information over the top of that block data. That's where file systems and object stores come in. So there's a positive future for file systems and for object storage. And file system protocols are maturing and becoming more capable. Those protocols allow talking to file systems over a network. We've done this for years. We've got NFS. Version 4 is a dramatic improvement on its predecessors and allows much more in terms of flexibility, in terms of recoverability, and it is a real improvement on previous versions of NFS. We've got SMB version 3. And that, although it's a Microsoft-developed file protocol, is becoming more POSIX-like. And we're beginning to see features that allow us to run an application that we might have developed for Linux on a Windows system. Now that's an interesting development, and it means that we're beginning to see the importance of these high-level abstractions, of these APIs that allow us to communicate from application to application, and all we need to do is recompile it. We don't need to rewrite it. There are lots of interesting file system developments. We're seeing huge advances in terms of high performance and clustered file systems, like ButterFS, or BetterFS, depending on how you pronounce it, Ceph, GloucesterFS, and more. And if you think about it, with IoT, the Internet of Things, we're generating a huge amount of data at the edge. And again, file systems and this idea of a byte stream of data is very appealing. And file systems and POSIX have a capability to manage those devices remotely as well. Lastly, cloud and object type stores can't yet replace all the functionality that some of our applications require. Transactional systems, for instance, are very dependent on file systems. And stream-oriented data, which cloud and object stores is not terribly good at yet. They tend to deal with objects as big lumps. The cloud deals with large quantities of data. And in an application environment, we're very often dealing with small, discrete, and packaged amounts of data, and files are a suitable way of expressing that. So that's a brief overview of POSIX, why POSIX, and a little about POSIX storage and some of the advantages and disadvantages. But I believe that the advantages far outweigh the disadvantages. You're going to see an awful lot more work in terms of providing POSIX, if you like, for the future as we move into this Internet of Things and data streaming and treating this vast amount of data that we're generating at the edge and having to manage it. So, Rob, I'm going to leave you, last but not least, to do log structuring and other fun stuff, which sounds really interesting. Take it away, Rob.
Well, thank you, Alex. I appreciate it. Good commentary on POSIX and storage. So this is the final part of the webcast, and then I think Jay will take us through some question and answer as well. I have two topics for you today, which are, as it turns out, quite similar. They are related, but they do have some differences that I will outline for you. And the two techniques I want to cover are log structuring, or log structured systems, and then journaling. Again, related to log structured, but with some key differences. And maybe talk about some other fun stuff as well as we go through in your questions and answers. So let's start with log structured systems. Now, a definition that I think is very useful is where a system where all incoming metadata and data, so both parts, if you like, of what the file is or what the object is, and also the data about that file or object, are, instead of being written randomly over a set of blocks, and again, Jay went through blocks and files and objects, instead of being written randomly, they're actually written sequentially into a circular buffer, also known as a log, and hence the name log structured systems. Now, in history, this is not new, and in fact, it's nearing its 30-year point now. And it was first implemented in a system almost 25 years ago, a Unix-like distributed operating system called Sprite. And again, part of the rationale behind this was to try to overcome, back in the day, but also today as well, the inherent deficiencies in writing randomly across a block-oriented media, such, for example, as a rotating disk. But a lot of these techniques also apply to solid-state storage. So a non-log system writes randomly. In other words, it does overwrite in place. So if I have a block of data that I want to overwrite to a particular location, I'll just write it there directly. That's known as a non-log structured system, which was the original systems back in the day of block storage. As a difference, though, log systems actually take updates. So any new data to be placed on the system, and in particular file systems. Again, you may have already caught on to the fact that these techniques, log structure and journaling, are very useful in the file system context. But again, not necessarily restricted to that. There are other systems which take advantage of log structuring and or journaling. But the log systems actually batch up updates, and then they write sequentially to the log. Again, this is as opposed to writing randomly as the requests come in. So it's not an overwrite in place system. And more importantly, writing data in a log-structured manner enables several things that turn out to be a benefit of this particular type of architecture, some of which are crash recovery. In other words, you always know where the end of the log is. You're keeping track in your system where the end of the log is. And then also the ability to checkpoint or to take a look at where I am in the order of writes, and write ordering is important in lots of systems, log structured included. So I know when the last good known persistence was. So again, this is a stateful type of approach. We keep state, so we always know where the last known good persist to the media is. And then we also have the ability to roll forward through the log from any given point in time up till, of course, the end of the log, and do what some folks call log replay. So that's an overview of log structured systems. Again, these deal with both metadata and data in a single go. Now this slide is a bit busy, but it does cover a basic operation about a log structured system, which is captured on the left side of the screen, as opposed to a non-log system or a typical file system that would be used in an operating system, for example, like Unix. This is actually taken from one of the original papers on log structured systems. So starting on the left, you can see the differences in the log approach where files and their directories, and directories are, again, metadata, information about files which are in a directory, and they are written to sequentially down the log with the arrow indicating time. Time is the most important element, of course. We want to keep things in order. So if you imagine the surface being a disk, but it could be any other persistent media, as I write files and directories, either updates or new information coming in, I write them in a sequential manner. So all the information about a given file and its directory is kept together in terms of the ordering of the blocks in the log. And the log, of course, always moves ahead in time. This is as opposed to the more traditional file system approach, which is an overwrite in place, a non-log, where files and directories may be scattered in their inherent blocks. Again, as Jay mentioned, a file could be one block or many blocks, and that also applies to the metadata. The metadata could consume one or several blocks on a persistent media. So you see they might be scattered about, and writing and changing file 1 and file 2 may end up with random seeking across a media. Again, on a rotating disk, this is not necessarily a good thing. So that's, again, that's an overview of the basic structures involved in logging structured systems versus a non-log. Okay, now one more aspect about log structured systems is how to clean up. In some parlances, this is known as garbage collection, or GC. And there's really two methods if you embody a log structured system, say for the purposes of a file system. Again, one of the most popular ways to do it, that you can have a threaded log where the old login and the new login are always known. And we're taking care to overwrite or manage the deleted blocks. When I delete a file, of course, that information is no longer useful. And that delete operation, of course, would be one of the operations in the log. So again, the keeping of state, the moving of pointers, and keeping track of where the blocks are, what blocks are active, what blocks are not active, and then establishing a new log in. That's a threaded log. There is another technique called copy and compact, again, which involves taking the old blocks, making sure that we persist the old blocks in order, and then those active blocks are rewritten into another part of the log to make sure that they are contiguous in terms of block space. So this means adjacent LBAs, if you like. And then when that operation is done, I can delete the old blocks, move the pointer to the new login, and again, that's called copy and compact. And this turns out to be important because as the log moves forward in time, of course, some information is going to be stale. We want to overwrite or remove that so we can take advantage of more space in the log. Okay, let's quickly go over journaling systems. Again, these are related to log structured, but are slightly different because in journaling, the metadata, in other words, the data about the data, the metadata and the data itself are recorded typically in two different places. And again, a file system is a very common deployment method for journaling systems. There are many known file systems which keep a journal. You can see them on the screen. They're very popular. They're very well known. They've been around a long time, including the split journal technique, where the journal and then the data itself are kept on physically different devices. So we won't go into that, but again, that's part of a journaling system. Now, a journaling system is unlike a log-structured system in that it performs what is known as a two-phase or write-twice commit. So I'm handling the metadata as a piece of information to be persisted, and then in conjunction with that, its accompanying data, if any, is handled in a different manner, and again, in a split journal case, on a different device entirely. So in comparison with a log structure, the journal is really what I'll call only half of the file system. The journal is all about the metadata, and then the data itself, again, can be treated separately, and we'll go through an example on the next slide as well. Now, like its cousin, the log structured system, journals can do crash recovery, in other words, known as journal replay, where we're looking at the transactions in the journal and have the ability to replay them. We also know what the last known good persistent state is. Again, a journaling system is an example of stateful, so it goes right along with POSIX. And then journaling systems have this interesting feature called a barrier. And if you know your file systems, you know this. And a barrier is essentially a point in time that the application can deem where the journal and its accompanying data are synchronized. In other words, they're all caught up, and the journal is at a known good state, and all its data has been persisted to the media. We know this, and then we can carry on. So somewhat like a checkpoint, but a slightly different technique. Okay, here's an example of a journaling system. ext3, for example, is one of the better known journaling file systems. And ext3, as it turns out, has three different modes of journaling: write back, ordered, and data. And you can see in columnar order with time with the big arrow going down. So if you look down the slide, that is the advancement of time. Again, very important to keep order in any file system. So, for example, in the write-back mode, I've got data and I've got a journal, or an inode in file system parlance. The data itself is a fixed known location. In other words, it has an LBA, and we can go ahead and write that. But the journal, on the other hand, we want to take in the data, and the data is typically in volatile memory, and then that data must be committed to the disk. And when I say data, I mean the contents of the journal. So this might be, for example, if you do a POSIX open, you are actually changing the metadata of the file, not necessarily the file data itself. For example, one of the attributes might be last known access time. And if you're keeping track of that in your file system, you are effectively doing a write, you are doing a persist to capture that metadata. And that's what the journal commit is all about. So in write-back mode, once that journal is known to be committed, then and only then can I change the file system, the inode, and make sure that the metadata is up to date along with its data. So that's called write-back mode. On the other hand, over to the far right, the so-called data mode takes both the inode, or the journal metadata, and the data in one go, makes sure it's synchronized, and then and only then commits that to the journal. In other words, the record of the transactions that has happened. And then it does the write for both the inode, or the metadata, if you like, and the data itself, and treats that as a checkpoint write. So in other words, the journal does not advance until that checkpoint write is complete. So hopefully that gives you an idea about journaling systems. Again, they're very popular, they're very well known, and they have very good recovery characteristics along with log structuring. So hopefully that was fun for you. And as it turns out, we do have a bit of time for any questions and answers or commentary by Jay. So Jay, I'll hand it back to you.
Thank you. Actually, at the moment, I don't have any questions to ask, other than a comment that I really like the way that you tied this back in with the POSIX and the addressable sections as well. I would like to recommend that anybody who's listening, if you do have questions, now is a perfect time to start asking them. Because we've jam-packed a lot of information in here today, and it's actually amazing to think about how much ground we've really covered. Well, first we talked about the fundamental storage types in the data center applications, both block, file, and object. And we talked about the different ways of addressing those storage types. Specifically, we've talked about how byte addressable and logical block addressing are going to be playing a larger role with new and advanced storage types like persistent memory. We also talked about one of the mainstays of storage, POSIX, and explained how it's an access point to sources of data in both a random access and a stream-oriented function. And then finally, Rob took us through the different techniques for keeping track of writing and reading that data and making storage systems more resilient through the use of these techniques. And even though these may seem like discrete elements of storage, hopefully at this point in time you can now see how they all interconnect. And it looks like we just got a question here about objects. Does an object always have to be replaced in its entirety? How do systems handle updates to large objects? There are different ways of approaching object stores and how objects are appended or updated. And the answer of always is not necessarily the case. Most of the original object stores were all done by simply writing an object in its entirety and then changing the pointer to that new object, which is why we came up with the idea of calling these eventually consistent systems, where it was possible to get an earlier copy of an object by accessing it before it had a chance to be updated. Some object stores at this point in time are now much more synchronous, and they've created additional means of updating at a faster time frame. So there are differences between the object store systems, and I recommend that that you take a look at the ESF presentation and the object presentation that SNIA has done on Byte Talk as well.
Hi Jay, it's Alex here.
Go for it.
Just quick comment on that, and this may be something that takes us perhaps a bit beyond the level we were aiming at. But there's one true thing: any object store that takes a lock and locks a record isn't an object store. You can't lock in an object store. And what we're beginning to see in terms of updating objects are techniques that allow objects to be updated without locking by actually understanding the time sequence in which the updated parts are being addressed. So there are techniques for doing it, but none of them take locks. Now the POSIX solution is take a lock. And that's always the way it's going to be with file systems. Object systems don't take a lock, but there are ways that are lock-free that allow you to update objects. For instance, there's a technique that people may want to go and look at. It's called vector clocks. That allows you to, if you like, decide who wins in terms of updating an object. So the answer to that question as well is the subtle one of POSIX takes locks, object systems don't.
Excellent summary. Thank you for that, Alex. I really appreciate that. And we've just got some really great questions that came in that unfortunately are going to take us well beyond the time frame that we've got. Questions about flash versus NVMe, the load store access, persistent memory, a lot of stuff in there. And I think we're probably going to have to wait. I apologize. We're going to have to wait until that gets answered inside of the Q&A blog, which will be following up subsequently to this presentation. Some of these are actually addressed in other webinars, which we will give you links to in further detail as part of this Q&A. So I apologize that we won't be able to get to those in any kind of detail for this section, but we do have the answers for them, and we'll be able to give you the links to additional information as a result. So given the fact that we are running out of time, I do have a couple of things that I wish to try to convey to you. First of all, this is just one of many of the Too Proud to Ask series. Our next one, Part Turquoise, is going to take a look at the storage media itself. It's on August 1st, and you can register at the link below. Of course, it may be on the screen too quickly, but we'll be posting more information about this in the SNIA ESF blog and on our Twitter account. Of course, you will also be able to see this URL by downloading the presentation, which is currently already available on our webcast's webpage. This is, of course, just one of the many webinars we've done on basic storage terms that you may or may not be familiar with. And we're always looking for suggestions for more subjects as well. Now, obviously, as you can tell, these popular webinar series only briefly are able to cover some of the subjects here, and we'd love to hear our own selves talk, but we also know that your time is very valuable, so we're trying to keep things in kind of short snippets. But we're always looking for more suggestions, so please feel free to offer ideas in the questions or the comments or the ratings. Now, one of the things we haven't been able to do in this series, though, is show you how the pieces fit together to affect performance. For that, we have another series that you might find very useful, the Storage Performance Benchmarking series. When we start looking at storage and we hear about how people talk about how fast their systems are, it's useful to understand what exactly is being measured. And so this excellent series on storage performance benchmarking is one of our most popular, and it's full of great vendor-neutral, technology-focused information that helps put a lot of this stuff into context for you. I highly recommend that if you want to go to the next level and find out how all these things fit together, this is the series that you're going to want to take a look at. Finally, please rate this webcast and provide us with feedback. We love the feedback, especially knowing what we're doing right as well as what we can improve upon. As I mentioned during the course of this webinar, a PDF of the slides are available by going to the website. The link is here on this particular slide. And a full Q&A from the webcast, including those questions that we were not able to get to today, is going to be posted on the website, including links to additional information so that you can further your knowledge about how storage works. And then, of course, upcoming webinars and information about storage is going to be announced on our Twitter handle as well. So if you want to find out about the latest and greatest announcements about our educational series, as well as other things going on inside of SNIA, please follow us on Twitter at the SNIA ESF handle. Finally, these and many more storage terms are available by going to the SNIA dictionary. Of course, our webinars are designed to help flesh out some of the ideas of the storage dictionary. So if there's anything you want to have more explanation or you're more curious about, please feel free to contact us and make a suggestion. And finally, thank you for your time. We hope you've enjoyed the webinar. And on behalf of Alex, Jor, Rob, myself, and the entire SNIA team, we hope that you have a great day and that you've enjoyed these webinar series. Thank you very much.